Right, let's go. So, this is some research I've been working on for the best part of too long, a year in my spare time between things. And it's all about the single packet shuffle, digging for desync-powered request tunneling. If literally none of that makes sense to you, it'll probably be okay. We're going to go through most of it in as much detail as I'm able to fit in the 35-40 minutes that we have. And if none of it makes sense, well, follow along until the case studies at the end and hopefully you'll have some fun. Anyway, I'm going to be talking about a bunch of different things today. We're going to be talking about the breadcrumbs of research, what request tunneling actually is, specifically in HTTP2, fixing the existing tunneling detection that exists. There's lots of toolkits out there. We're going to fix a particular one. Something that I've coined the 2000 request problem, which is pretty funny when we come to it. Building custom tooling for your own web security research, if you'd like that kind of thing, including building a research pipeline. Then we'll go on to some case studies, and as all good research should, we'll wrap up with some other things you could try that I think might work. And there are two core references to this entire kind of presentation and paper, which is how to be a security, or so you want to be a security researcher, and building custom research tools, both from Portfolio. They kind of helped me out a lot with how to actually try research for the first time, kind of, and how to build tools. So both those blogs are worth a read if you're interested. So, all good research starts with some breadcrumbs. Things that you can follow that will lead to the kind of, maybe this is something more than it's already known about the industry, maybe there's something new here. And for me, it started with this. If no one recognizes that, it's a ping from a tool called HTTP Request Smuggler. It basically says, hey, I think you've got a request smuggling vulnerability, which is popularized relatively recently and can lead to all kinds of critical things. You should go look into it if you haven't. I looked into this ping on a bunch of different apps and quickly was like, nah, it's false positive. The way this detection works is basically to cause a delay in the response with a specially crafted HTTP request. And it's pretty prone to false positives, especially these days. And the way you confirm it, I had tried to follow the full methodology and it just wasn't working. And then a couple of days later, I got another ping. And then another couple of days later, a colleague said to me, have you seen this vulnerability before? Can you do anything with it? And then that kept happening. And each time I looked into it a little bit more and got absolutely nowhere. And I decided that it was 100% false positive, you should ignore that ping, and there's nothing you can do about it. And as far as I'm aware, that's what everyone else has been doing for quite a long time with this specific ping against certain servers in testing. However, as is often the case, one of my talented ex-colleagues, Axel, came to me with exactly the same thing, and he'd actually taken it a step further. He'd not determined that it wasn't necessarily a false positive, but he had some interesting behaviour that you might recognise if you're a big HTTP2 nerd like me. This request basically shows that if you send a request, a HTTP2 request, with both the content length and the transfer encoding header, with a really weird body that just says foo, and there's two new lines after it, you'll get what looks like a HTTP2 response with a HTTP1 response in the response body, which to me made absolutely no sense, because this is actually a very strong indication of something called HTTP request tunneling, which we'll cover now. And you can see how I highlighted it. Super weird. If you ever see HTTP2 with a HTTP1 response in the body, you've definitely done something weird, and they are definitely doing some funky things. So, let's go through what HTTP request tunneling actually looks like. Let's start with desync attacks. Desync attacks have been popularized over and over and over again by various people at this point, but they all rely on the same thing. I want you to imagine that you have a front-end server and a back-end server. In this case, we're just using HTTP 1.1. Because there are two different ways to represent message length in HTTP, you can have the content length, which is on the left-hand side, and the transfer encoding header, which is going to be on the right-hand side. If you use the content length, this request says that all of that stuff that's still highlighted is in the body. So from the 3 all the way down to the example.com host and the 2 new lines. That's pretty simple, right? It's just 50 bytes of data in the request. However, if the front end uses the content length and the back end uses the transfer encoding header, which is completely RC compliant, you should prioritize the transfer encoding header. The front end is the naughty one in this case. The back end thinks that the entire body is just the x equals y. That 0 and 2 new lines basically represents the end of the body in HTTP1 for a transfer encoding chunked request. Meaning that this extra data at the end, the flow onto the back end, is a completely separate request. Okay, so the front end thinks this is all one big request, and the back end thinks that this is two requests. And this kind of desynchronization between how different servers interpret message lengths in HTTP1 causes request smuggling and, as we'll now find out, request tunneling. Request smuggling is much, much, much more known about, and the main difference with request tunneling is that rather than sharing a single connection between the front end and the back end application, every client gets their own connection between the front end and the back end. If you don't already know, what front end servers often do is create what are called keep alive connections to back end servers, and rather than continually opening new TCP connections, which is really slow and not resource intensive, but it's just slower, they'll just keep that connection alive, hence keep alive. And you send data back and forth on this kind of tunnel between the front end and the back end. In HTTP request smuggling, you just have one line between the front end and the back end, or some pool of connections that all users share. And that's really dangerous, because when you leave prefixes, like we saw on the previous slide, extra data on those tunnels, on those connections, you can basically influence other people's requests. With request tunneling, however, the architecture is that each client, even if you share the same public IP address, even if you're both on the network A or the network B, you have your own connection between the front end and the back end. So your requests never go anywhere near any other users' requests, which sounds super secure. And actually, lots of popular front-end servers dynamically switch to this behavior when they detect people trying to do request smuggling, thinking that it will save them. Unfortunately, it doesn't. Request tunneling is a vulnerability that you can use to exploit this architecture. In particular, most easily in cases where you have a HTTP2 server that downgrades to HTTP1. And you might be thinking, well, no one does that. Actually, most of the web does that. All the popular front-end servers basically support HTTP2, and a lot of the back-end servers are starting to implement HTTP2, but for backwards compatibility reasons, usually run by default in HTTP1. So your client and front-end are speaking HTTP2, and your back-end is going to be speaking HTTP1. So what actually happens is, if you're trying to exploit request tunneling, is as a client, you send a request that looks like this. This is a HTTP2 request, so the content length and transfer encoding headers are completely irrelevant. HTTP2 has a built-in length mechanism that basically is a little bit in the frame, I think, which just says how big the frame is. So these headers are meaningless in HTTP2. You could probably just ignore them, but they're kind of kept in for fun. And then you add a 0, which represents the end of a request. It doesn't in HTTP2, but we're just pretending it does. And then you have a full request in the body, which is this, in this case, a get to a 404 page. The client sends that to the front end. The front end uses HTTP2 and says, yeah, that's one full request, no problem. It then flips the language into HTTP1. It changes it from a binary to a plain text protocol, the details of which you don't really need to know, and then forwards it on to the back end as is. You can see the front end is basically sending all the body data. It's not leaving anything behind. It knows that data is all part of the body of the initial request. Now, once it gets to the back end, things get tricky. Now we're talking HTTP1. So these headers suddenly have a lot of meaning. And let's say, for argument's sake, that the back end chooses to use the transfer encoding header. It knows it's a post request, so it needs to look at the body. And it reads in the data, says, oh, there's a chunked encoding, cool, I'll read up to here. That's the end of the request. It says so. It says 0. It's the end of the request in transfer encoding, and therefore thinks that this is the start of the next request. So, if the backend has 2 requests, what do you think it does? It responds twice. Why wouldn't it? It's got 2 requests. They're 2 separate bits of data. So it responds twice and streams that data back to the front end. The front end, having issued 1 request to the back end, expects 1 response from the back end. Seems fairly standard. So basically, it takes what it thinks is just like a big stream of data. It doesn't know that there are 2 responses here. It just receives a bunch of bytes in a row and goes, okay, and stitches them together. And suddenly, you have a HTTP2 request with a HTTP1 response in the body of the response, and that gets sent back to the client. You have now successfully tunneled a request past the front end that the back end actually interprets, but the front end completely ignores. That doesn't sound particularly dangerous until you start to think about the fact that access control rules can be put in place on the front end, which now no longer apply because the request is hidden in the body. Access control rules tend to apply to the request itself, the headers, and not the body of a request because it's just very hard to do. Silly. So, now that we know what request tunneling actually is, there's a really, really great tool for detecting it called HTTP Request Smuggler. This has been invented by Paul Swigger. It's really, really, really good. And it was where I found these kind of strange pings that I thought initially, for months, sadly, were false positives. It actually has built-in detection for request tunneling. And because I'm just that lazy and I don't want to manually check for request tunneling every time I test, I thought, well, what's actually wrong with the detection they had? This is the detection method they're using. It looks very similar to the request I sent that had foo, except it has bar and R at the end of it. I guess representing like the method path and HTTP version. It's like a kind of vaguely invalid HTTP1 request. But in the case I was working with, this never ever responded with HTTP1 response in the body, and therefore the detection just failed. So I kind of grit my teeth and decided I'd take a look at the Java code that was used to write this tool. And it's very simple, as it turns out. There's a scan file called headscan.te, probably headscan transfer encoding. And on the left you can see that there's a string called foobar, which looks like the payload you're supposed to send, and then just add it to this list or array called attacks, maybe. I don't know much about coding, but that seemed about right. So I just added 2 new lines to this tool, which were an attack called foo, which was just foo and 2 new lines, and then added that to the list of attack methods. And then I ran this new detection method against all the apps that I'd found that I thought were false positives, and it worked 100%. I thought, hey, that's a really easy new little novel security technique for detecting things. Not bad, not quite, not amazing, but you know, it's new, it works. That should be in Request Smuggler very soon. And it worked against all those cases that I thought were false positives. So now that detection was working, I figured, hey, let's exploit all these new vulnerabilities that I found in our customers' environments. However, I quickly ran into a problem that I've called the 2000 request problem. When doing request smuggling, or tunneling even, you'll often find that when you're doing the detection, you instantly get back a tunneled HTTP response. And it's really, really quick, really, really fast, which is great. But the second you try and actually do an exploit, so you're going to smuggle or tunnel an entire request to the backend. So the first one is just kind of like part of a request, it's very invalid. The second one is a whole valid request. It basically would take like 2,000 requests for me to get one single hit back. And that takes a lot of effort. You've got to send that request on the left over and over and over and over again just to get one valid response back, which is really, really tedious. And I got stuck on this for months with all these cases. So I thought to myself, what the hell is causing this inconsistency? It makes absolutely no sense. And I kind of forgot about it for a while, and then on a train, looking out the window when it was raining and thinking down to Plymouth literally to see my parents just down the road, I decided I'd have a think about it out loud, which I must have looked absolutely mental, but I was just saying these phrases to myself in my head. It takes thousands of requests to get one successful hit. That's kind of weird behaviour in itself. Thousands, tens or hundreds maybe for request smuggling, but thousands, completely impractical. It's a lot of data to be sent in. It's also, so it's inconsistent, but it's inconsistently inconsistent. Sometimes it would take 2,000 requests, and sometimes it would take 2. It would just suddenly work, and I had no idea what the hell that meant. Now, the astute among you may know what this kind of behaviour describes. Something that's really, really inconsistent, inconsistently inconsistent, and very hard to recreate. And I kind of thought to myself, wow, that's kind of maybe a race condition, but it can't possibly be a race condition. That doesn't make any sense. It was a race condition. Fortunately for me, web race conditions just got made incredibly practical that year at DEF CON and Black Hat with something called the single packet attack, hence the single packet shuffle. So, for those of you who don't know, the single packet attack basically fixes web race conditions. For a race condition to occur, these 2 requests have to hit the race window at basically the same, sub-millisecond, but we'll say millisecond for argument's sake. And all these things get in the way. Network latency, jitter, internal latency, dumb luck, bit flips, whatever. Who you pray to, for example. The single packet attack fixes this by basically bundling, 20 or 30 requests together, sending most of the data and withholding just the last byte of data. and then it sends that last byte all in one single packet. And the application server is very unlikely to actually start processing that data until it receives the full request. So, when you send them in the single packet attack, you remove network latency and just almost entirely, internal latency is likely to be significantly more consistent, and your race condition windows line up significantly more often, which is very, very useful for trying to exploit race conditions. So, my solution to this seemed obvious. Let's see if I can use the single packet attack to make my new method of detection and exploitation of request tunneling super, super consistent. So that's what I went about doing. Unfortunately, not only is a single packet attack relatively simple to kind of understand, for just syncing up the timings of the requests arriving at the server in some technical way, it's also extremely trivial to actually implement and use. In Burp Suite, you can basically add a bunch of requests to a repeater group. So you have like 5 requests in repeater, put them in a group, and then select send group in parallel. So this is what I tested. I took this exploit request, which is, there's just 2 here, but you can imagine kind of up to 30 of them, with the attempt to tunnel a request in the body of the HTTP2 request, and sent them as a single packet. And instantly, I got a successful hit back. This actually worked. Still blows my mind today. So some kind of strange combination between race conditions and request tunneling exists, and I haven't read anything about it, so I think it's pretty cool and pretty new. As a result of this, I think this worked kind of so consistent that it was kind of 80% consistent. You only had to try this kind of a few times in a row for it to get a hit, which is a lot better than sending 2,000 requests. Now you're sending kind of, well, 1 packet in theory, but 30 requests down a tunnel. Now, this made exploitation significantly easier, but my brain, as a tester, as a lazy person, as a researcher, thought, hey, if this works for exploitation, maybe it also works for detection. I will improve the detection, maybe I can improve it further by just sending everything in the single packet attack. So, let's build a custom research tool, because that doesn't exist at the moment. Fortunately, as the lazy tester I am, I'm also a lazy programmer. And I don't want to go about building tools that can scan lots and lots of targets. So I went and found one. If you haven't heard of bulk scan, it's in basically all of Portswigger's research tools. It's on GitHub, of course, and it basically allows you to bulk scan things. It allows you to select kind of your entire Burp proxy history, regardless of size. Well, okay, there are some soft limits to memory consumption, something like 100,000 requests, but in theory you can just select as much data as your RAM will handle. It will then deduplicate similar requests and responses based on keys. So like if the server header looks exactly the same, and the request path is exactly the same, and the request parameters are exactly the same, probably don't need to scan those 2 requests, you can just scan one. So it will deduplicate that for you. Each scan runs in its own thread, so you haven't got to do any of the magic that people do with threading tools. And the thread count is completely customizable, so if you have a nice powerful laptop, and that's all you need, you don't need like a huge research machine, you can just whack that thread count way up. And you can also combine it with a tool called Distribute Damage, which allows you to apply a per host rate limit, which is really important when you're going to scan the internet. Otherwise, people get angry at you because you're sending lots and lots of requests per second. Instead, you can send like 200 requests per second to 200 hosts, and then you wait 5 seconds and do it again. So you also bypass rate limits, which is really, really handy. To actually implement a scan into bulk scan is also fairly trivial. My idea was to take all the existing permutations from HTTP request modeling. If you don't know what those look like, they're kind of weird, non-RFC compliant versions of the content length and transfer encoding header. So you have spaces in weird places, backslashes. They should be rejected, but HTTP servers love to be helpful and just accept them anyway. And there are lots of different ones out there. So to actually code this, the only code I actually wrote is basically a little class that says override the do-scan method from bulk scan. And then for all the permutations I've written, create a request, or take the request from the proxy that you're scanning in this particular thread, apply the permutation, which just means replace the transfer encoding header or the content length header with the permuted header, then attempt to send that new exploit request in a single packet, and then go through all the responses from the single packet attack, and if any of them contain an HTTP response, report an issue in Burp. That's literally it. I also, because I struggle with Java, took bulk scan, imported it into kind of a template, and rewrote it in Kotlin, which is basically a very Pythonic version of the Java in a sense, which means that if you go to my GitHub, you can build research tools and you basically just get dropped into this class and you can just interact with the Montoya API, which is really, really, really easy. This code isn't far off the actual code I wrote, genuinely. So, from there, I had a research tool that I kind of thought would be interesting to run against lots and lots of targets. Of course, now I needed lots and lots of targets, and you can't just go scanning the internet. In general, you can, but this is vaguely malicious. It could trigger things that I don't want to trigger. So what can I legally target? Well, bug bounty seemed like a good start. This is a common technique. You take a tool like Bug Bounty Scope, which will just take all the scopes, like HackerOne, Crowd, Integrity, whatever it's called, a couple of other big ones, and dump them into an Excel file. And then if you're being kind, like I was, you go through the hundreds and hundreds of entries manually and check if they allow for automated scanning. Lots of them don't. That took a long time. Once you have a list of scopes that you're actually going to be allowed to scan, you can then take some DNS data. I think Project Sonar has a database of every known hostname ever, but I don't have access to that. I'm not really sure how I think you just have to email them and say, very nicely, I'm doing a research project, but obviously what I wrote wasn't very good, I don't know. But there is an open source one from Project Discovery, of all people. It's a DNS database of all the bug bounty data. So I can take kind of 5 million domains from this huge amount of DNS data, map it against my scopes, check how many of them are actually alive and running HTTP, which is about 150,000 alive domains that I'm legally allowed to attempt hacking and automation against, and then pump them into one massive sweet file that I can run my tool against. And then you select everything in proxy and hit scan, and you pray. And I got some hits, and then I got some more hits, and I was like, this works. And it really did. I'm making good time. This is good. I got a ton of cases, so many that by the time I had reported to the 2 key vendors involved in, which is as early as I could, in the process, I ran out of time testing them to try and find interesting things. And request tunneling is really tricky to exploit, but I've got some examples for you to try and hammer home the idea that this really can lead to some very bad things. And the tooling for this, I'll come back to that in a second. So, we have a research file, we have a ton of cases on legally hackable targets, we have some novel techniques using the single packet attack to trigger request tunneling. What can we do? Who was actually impacted? Well, like I said, there were 2 key vendors that would be in front of or sharing the same kind of backend. And fortunately for me, they were quite interesting case studies. The first was Amazon Web Services. Amazon's application load balancer does downgrading by default, and when attacked with a single packet, flips into some I'm receiving a lot of requests mode, so I'll chunk all the data I'm receiving. It still does this after the fix, and I don't really know why. I have asked, and they never really respond to that part of my email. So, regardless, this example is from a real bug bounty site that I actually managed to exploit. They didn't really care much, but I think it's a great example. I want you to imagine that we're sending a GET request to the admin panel, which obviously I'm not supposed to be able to get access to. And I can see that the AWS load balancer was getting in the way and saying, no, you're going to admin, I'm going to redirect you away and say, error, bad, don't go to admin. And that's totally fine. But of course, with request tunneling, since the rule applies to the encapsulating request, so to speak, I'm not sending a request to admin, I'm sending a request to the homepage, and I'm tunneling a request to the admin panel. And when you do this, Amazon's web, application load balancer will look at the request and go, okay, no request to admin there, that's fine. All the data, all the kind of stuff that we just talked about with request tunneling and the single packet attack happens, and you get a response with 404 versus 402, and then the admin panel in the body of the request. Now, of course, you can't render it, but you just have to kind of interact with it over and over again, and you can do all kinds of dangerous things because you're just completely bypassing the access controls that they've put in place in the front end, which is good fun. Additionally, this isn't the only kind of access control that you can put in place on the front end. This is the most common one. You just set a path that you don't want people to reach, and you assume that the front end is enough to protect against it. Request tunneling just totally bypasses those rules. Front ends also rewrite headers for you. So, this one's a little bit more complicated. I want you to imagine that this pseudocode is running on the back end. And it says, for the root, I've got highlighting, I did good for me. The root admin has a function that says, when a request arrives, if the x-forwarded4 header is set to localhost, which just means the machine that the server is physically on, someone locally sat there, so probably someone with high privileges access, then return the template that's actually the admin page. Otherwise, if it's any other value, just respond with a 403. So it's a kind of access control that you can have in place. That just says, if someone is physically at the server, give them access to the admin panel. Otherwise, if you're coming from any other IP address, you can't access it. By the way, that's probably an important point. The x-forwarded4 header is added by front ends to say, this is the public IP of the request, the originating request. So I request something, it will say my public IP, so you can do naughty things like tracking people. So, when you send a request like this from the client, the front end basically adds the x-forwarded4 header with my public IP address. This isn't really, this is random. And then the back end receives that, runs the code, and returns a 403. Since the x-forwarded4 header added by the front end does not equal to localhost. Okay. It seems like a pretty secure pattern for the most part. The x-forwarded4 header represents the public IP, and the back end just interprets it and says, yeah, you're not coming from localhost, so I'm going to reject the request. If you're a pen tester, or just maybe slightly creatively minded, you're thinking, why can't I just have my own x-forwarded4 header as a client? And you can. So if I send a request like this as the client and say, hi, I'm coming from localhost, trust me, it's fine. The front end will go, no, you're not. And it will rewrite the header. Okay? And it does this by searching through the headers in HTTP2 and saying, no, I'm going to rewrite that header. I don't care what value you give it. Now, of course, while the header gets rewritten in the headers, there's a place where it doesn't get rewritten. So with request tunneling, what I can do is send a request like this, and I have the x-forwarded4 and localhost value set there. The front end goes, hey, I'm going to add my x-forwarded4 header to your headers, and then pass it on to the back end. This one gets left completely untouched. So it reaches the back end, and then you also access the admin panel. So both of those patterns basically allow you to bypass access controls. Now, you might be thinking, how do you know that an application is even using the x-forwarded4 header? How would you ever kind of get that information? Well, you can just read documentation for one part. They'll often front ends AWS state the headers they add, HTTP scheme, x-forwarded4 or x-forwarded host, x-forwarded port maybe, x-forwarded protocol, whether you're using HTTP or HTTPS, all that kind of stuff. But also, you can use a tool called Brand Miner to just guess headers. And actually, Brand Miner has an integration where it works with request tunneling. So it will guess headers in the tunneled request and see if the tunneled response makes any differences. So you can quickly figure out if any headers kind of look interesting, and then you can mess with them to see if you can bypass interesting stuff. Of course, that doesn't work when you have to use a single packet to attack it. So I took a really rubbish version of that code and tried to stuff it into my, like a binary search to my tool, which is all public, so if you come across this, you can definitely use it. I did manage to get a real case using that, but the tooling absolutely works. I know for sure in a lab that I made, so hey. So other than AWS, what was the other vendor? Oh, sorry, let's not move on too quickly. AWS Fix. AWS were awesome. There's no bug bounty program for the cloud services. I mean, there is one, but it's a disclosure policy. It's not a paid one, which is fine. I reported it to them. They basically immediately communicated out some mitigations, which is to set, I think, the Desync protection to strict. And it would basically be more strict with the way it passed these vulnerabilities, all these requests. They deployed some telemetry, updated some documentation with new Desync mitigation classification, which is cool. It's not credited to me, but it's my fault, which I'm happy about. And then in March of this year, they deployed a fix. And if you're wondering, the redacted thing in the program was this custom, but they happily were able to let me unredact that. The fix is pretty simple. If you send a request to any application load balancer from AWS now that has a transfer encoding header with a space before the colon, you just immediately receive a 400 request and it just drops. So far as I know, that fix is working. I haven't been able to do anything with it since, so good job. They were very nice about it. Since it works on AWS, I figured, let's see what else it works on as I'm scanning. And a few of my cases were from the other one. Azure, front door. I still don't know why this worked. They actually weren't vulnerable. I could tell that it was Azure because they had X Azure ref, which is a known header from Azure. And I had a case where my normal single packet detection worked. It actually didn't even require the single packet for this one, which is kind of interesting. But also, it was only one server that actually responded this way, which is kind of interesting. The rest of them were just vulnerable to kind of regular request smuggling, which is quite similar. It was connection locked, so you couldn't affect other users. So it's effectively very similar to tunneling. You can only bypass kind of front-end rules, and you can leak internal headers and do other fun things. I've not given an example because it's basically the same as what you just saw. But effectively, you send a request that looks a bit like this. Rather than smuggling an entire request, you're just smuggling a prefix, and then you'll receive a bunch of 200s and then 404, and that 404 could be, for example, the admin or whatever rule you wanted to. You again have full control of the request that you're sending and avoid any rewrites, which is also very good. I reported this to MSRC, and they responded with this big letter, which kind of boils down to, thanks very much. Not urgent. Request smuggling isn't a vulnerability on its own, which is maybe fairly. You need the kind of gadget. You need the back end to implement some code that is vulnerable that you can use, or the front end to have a rule in place. So I asked for some clarification, what kind of impact they'd like that would prove it, and I gave them the examples, and they just never responded. So this is my public disclosure. It isn't fixed as of last week when I last checked it. So if you want to go hunting for this, feel free. It works with the normal detection techniques. If you want some examples, I have my research file here. I can show you. If it's still working, you never know, they might have fixed it, but that's just what happens sometimes. So, let's wrap it up as quickly as I can. Some key takeaways. Request tunneling is still underrated. It was underrated before, it's still underrated now. Cases of it are hiding away. It's often blind. You get no kind of response back, or it's just really, really tricky to exploit because of the 2000 request problem. But there are ways to get around that. The single packet attack seems to work well. While it worked really well in AWS, it may still work in other places. I haven't found any, but the research tool exists on my GitHub if you wish to use it. And also all the tooling that I built exists on my GitHub. It might be private right now, but I'll make it public right after this. Building your own research tools for BERT is really not that scary. I thought it would be terrifying. I'm not a programmer, but thanks to bulk scan, you just kind of write just the scan check and then highlight everything and go scan. If you're interested in doing your own research, the two articles I linked at the beginning are really, really great. But also my biggest bit that seemed to work for me is when you follow the breadcrumbs, actually be the one to go back and say, maybe that false positive is worth looking into a little bit more, and then keep pulling the thread. And if you do, you'll end up building kinds of wacky tools that work and find you cool cases in cloud services. And like I said, tooling and resources available at my GitHub. And finally, as all good research should, let's wrap up with some further research ideas. Browser-powered request tunneling. Launching request tunneling from your browser with a completely HTTP2 compliant request. Not just a theory, that actually works. I haven't published my work on it so far because I really want to get a working exploit for it, but the detection for it is working, and there are certain servers that just ignore content lengths and allow for request tunneling. It's very fun, but definitely worth looking into. If you can think about how to build a technique to detect it, it's really easy. You can just go scan it. The single packet applied against other HP2 downgrading to HP1 implementations like AWS, Azure, Google Cloud Platform might be a good other target. Further methods of making request tunneling not blind. James Kettle's head technique is great. For some reason, this technique of just slightly shortening the request payload and making it foo also kind of made request tunneling unblind, which was super useful. I'm not sure if we have time for any questions, but thank you very much for listening. Check out our blog at Azure, check out my blog, and follow me on Twitter and all Blue Sky. Thank you very much. Any questions? Hungry? Yeah.
I think one quick one.
Go on.
Would this work against tall servers?
I hope not. I have no idea, actually, if the routing would be like getting in the way completely. I guess the packet just gets passed through all the different layers, and then depending on where it ends up, like if the first interpretation of it and the last interpretation of it, it would be what mattered. So maybe. Good question. Not 100% sure. You'd have to go scanning tool and find out. Let me know. Yeah.
Thanks.
One more. Sorry.
With it obviously all being front end, would you not argue that given most apps nowadays are secure by design, anything that could pose much of a vulnerability would be verified on the back end a separate way, not so.
You would certainly hope so. Yeah.
Well, yeah, you just
Yeah, that's an assumption, but I have learned to not make such assumptions. The example I gave, the very first AWS example, is a case of that. That's a real website on the internet that just trusted the front end tool, and especially the header exploit. A lot of servers implicitly trust front end header rewrites. Not necessarily for authentication, but for other critical things. There are some really, really bad examples published by James Cattle from Wallstreet. He owns the entire internal network somehow using the host header being rewritten. So yes, I assume people do add extra violation on the back end, but they don't, in theory, 100% of the time.
I also assume from Angela.
Sorry?
They also assume
that the front end's pretty solid because it's from Amazon. So yeah. Cool. One more, go ahead.
Are there any options for backend that run the HTTP to to deal with all of this?
It's not. Avoid downgrading. The fix to this is probably a good thing to mention. Is use HTTP2 end to end, 100% of the time. It's becoming a lot more common as I understand it, and I've heard some comments about CDNs being the blocker for it a bit. So yes, lots of backends do now support HTTP2, and they should use it by default, and so should all do. Cool. Thanks very much, guys.